Hello everyone, my name is Graham Dudgeon. I am an industry manager at MathWorks serving the utilities and energy industry. It's my great pleasure to be joined today by Patrice Brunel, who is a power systems engineer at IREQ Hydro-Quebec. The theme of this webinar is that you need an ecosystem for power system studies, a computational ecosystem. What do we mean by that? Well, when we look at power system studies that are being conducted nowadays, it's more than just about having a simulation model. The simulation model continues to be a very important part of power system studies, but you need additional capabilities and additional considerations. In today's webinar, we'll be looking at 6 aspects of this ecosystem. Patrice will talk us through the first 3 aspects, then he'll pass back to me and I'll end by talking about the final 3. We'll then summarize the webinar. So with that short introduction, I'm going to pass over to Patrice. Patrice, it's all yours.
Hello everyone, my name is Patrice Brunel and I am a power system engineer at IREQ, the research center of Hydro-Quebec, a major supplier of electricity in Canada. In this part of the presentation, we will be looking at 3 aspects of how we best construct simulation models in order to achieve certain objectives. The first topic of my talk is called Developing Simulation Model Suitable for Different Time Periods. We'll follow a discussion on developing customized simulation components. And the last topic is replaying recorded data through a simulation model. With simple system, you can develop simulation models that are relevant for simulation studies ranging from microsecond accuracy to capture power electronic switching, to hours or days to capture customer behavior and or variable energy profile over extended period of time. There are many examples in the simple system shaping demos that show different time regions of interest. Here are a couple of examples. When your interest is to simulate power system transient, detailed power electronics or fault studies, you normally perform simulation that run in the range of milliseconds or few seconds of simulation stop time. In such case, it is advantageous to discretize your model with the Power GUI block and use the fixed step solver of Simulink. The DC-DC and DC-AC PWM converters model is a good example, where the Power GUI is discretizing the circuit at a sample time of 5.14 microsecond of time step. The solver option of Simulink is set to discrete, no continuous state, fixed step type, and the stop time is 0.1 second. We simulate this circuit to catch high frequency switching of inverter that is generated by the PWM. When your interest is to simulate, for example, electromechanical oscillation or stability studies, you normally perform simulation that run in the range of seconds or few minutes of simulation stop time. In such case, you can use the continuous method of the Power GUI and take the advantages of the variable step solver of Simulink to gain simulation speed. Note that discretizing the model is still a good solution when your model is relatively large or contains several power electronic devices. The mechanical coupling of synchronous generator with exciter system is using the Power GUI in continuous mode. The OD23TB variable step solver of Simulink and the stop time is set to 10 seconds of simulation. The simulation shows the transient response of the generator following a fault on the speed, mechanical power, and machine voltage and currents. When your interest is to simulate microgrids, renewable energy, power quality, high-level strategy, etc., you definitely need to perform simulation that run in the range of hours or even days of simulation of stop time. In such case, the solution is to use the phasor mode of the Power GUI combined to the variable step solver of Simulink to gain an optimum simulation speed. The power microgrid is a good example that shows the behavior of a simplified model of a small-scale microgrid during a 24 hours on a typical day. The model uses phasor solution of Power GUI in order to accelerate simulation speed. Again, the variable step solver of Simulink are the preferred option. The simulation of the model shows a typical load change in ordinary houses for a 24 hours period, where the amount of electrical power load reached peak consumption at some point during the day. In this presentation, we are going to focus on simulation runs that cover several number of days, to not say a full year. In this case, the objective of the simulation is to observe longer-term behavior, and we therefore do not need to explicitly model power electronic switching nor consider electromagnetic transient simulation. Instead, we will concentrate on phasor simulation and look at the technique that we can apply to bring out the best simulation performance for this type of study. Our featured example is called 1 year simulation in 1 minute. It is a SimPower system simulation of an energy storage system used on a power grid. The objective of this example are to demonstrate SimPower system capabilities to simulate an electrical circuit, including control system, in phasor mode for a full year period in less than 1 minute. It also illustrates concepts related to energy storage system. It shows how to use public solar data time series and how to create typical load profile. The model can be split into 4 major components. First, the electrical distribution system, then the dynamic load model, representing residential load, the typical meteorological year solar data block, feeding power signal to the PV farm model, and finally, the energy storage system model. The electrical grid of the example represents a typical North American utility distribution system. It consists of a 120 kV transmission system equivalent supplying a 25 kV distribution substation. Several feeders are connected to the 25 kV bus of the substation. One of them supplies the power to a community that owns the PV farm and an energy storage system. Thanks to the SimPower system phasor solution, this grid can be simulated in a very short time, even if the simulation period is 1 year. Phasor solution is the ideal algorithm if you are only interested in a change to magnitude and phase of all voltage and currents in your circuit. You do not need to solve all differential equations resulting from the interaction of R, L, and C elements. You can instead solve a much simpler set of algebraic equations relating the voltage and current phasor. A special control block was designed to precisely control the fault breaker for a given day, hour, minute, and second. This block allows SimPower system to precisely capture the programmed transient to the millisecond precision. The second part of the model is the dynamic load. It implements a 3-phase, 3-wire dynamic load based on load profile. The active power P and reactive power Q absorbed by the load vary as a function of positive sequence voltage and load profile data. The profile are daily load profiles specified on an hourly basis. The third part of the model is the typical meteorological year data system. It converts solar irradiance data to power. This power signal is fed the SimPower system model PV farm that converts power signal to currents. The irradiance table data is modeled by lookup table that imports data from math file. The PV farm is modeled by control current source. Typical meteorological year data contains hourly value of solar radiation and meteorological elements for a 1 year period. These files have been produced by Henrel Electrical System Center under the Solar Resource Characterization Project. To view meteorological data in a given location, check this option on the block menu. The last part of the model is the energy storage system. It contains the following components: a control system, an unavailability monitor, a stored energy calculator, a SimPower system power-to-current model, and a step-up transformer. At any given time during the day, the control system determines the required power from the ESS in order to maintain the power below the specified value of the maximum power allowed from the grid. This power signal is fed to a power-to-current SimPower system block connected to a step-up transformer. Although the power rating and capacity of the modeled ESS are respectively specified in kilowatt and kilowatt-hour, as for a battery energy storage system, this ESS could represent several types of storage systems, such as flywheels, compressed air, supercapacitor, pumped hydro, superconductor magnetics. Obviously, a multitude of applications related to energy storage system and smart grid can be studied and validated using a SimPower system model such as this one. Application could be as diverse as financial energy arbitrage, line congestion mitigation, equipment deferral, solar power smoothing, spinning reserve, voltage support, etc. In our case, a simple scenario has been chosen to illustrate one use of this demo. The objective is to determine appropriate sizing in power and capacity of an ESS equipment connected to a 600-volt community electrical system in order to prevent the community from purchasing more power than agreed with the utility company. Based on a given load profile, PV farm output, ESS power rating and capacity, this simulation will give the number of unavailabilities for a full year. This sizing study can be performed for various locations around the United States. I'll start the simulation of this model. There is a display here that shows the days of the year. Another display here shows the number of unavailability in power and energy during the simulation. We can take a look now at the simulation result. We can see that we have almost half of the year already simulated, and we clearly see the different seasons of the year: the spring, the summer, and the fall, and the winter. And here it goes. We simulate a full year in, let's say, less than 1 minute, I guess. If I zoom to one of these unavailability here, we can clearly see that the community was unable to keep its consumption below the agreed limit of 1 megawatt and have no choice to buy more power from the utility grid. I will now redo the simulation, but just for the first 51 days of simulation in order to capture the tangent fault. I'll change the stop time to, let's say, a day after, let's say up to 51 day, and then start the simulation. Now I will zoom on the very last moment of the simulation to catch the transient at day 50. We can see here that I very precisely be able to look at the transient occurring for 0.2 seconds of fault. Developing customized simulation component. With simulation models which run for a long period of simulation time and or where you will be conducting Monte Carlo simulation, you may want to consider removing and or refactoring algorithm in library blocks for a given simulation run. The example we will be looking at is a microgrid simulation which includes solar, wind, and electric vehicle integration. This model is called Power V2G and is included as a shipping demo with R2015A. The microgrid is divided into four important parts. A diesel generator, acting as the base power generator. A PV farm combined with a wind farm to produce renewable energy. A vehicle-to-grid system installed next to the last part of the system, which is the load of the grid. Let's take a closer look at the load subsystem. You'll notice that the asynchronous machine is appended with the word customize. We made use of the power customize to allow us to modify the library block in order to improve simulation speed for large time step phasor simulation. The electrical model of the machine was modified to remove the saturation model with the purpose to gain simulation speed. We now start the simulation. There is a display block here that shows the running hours. We can look at the simulation result in the total power scope. The simulation lasts 24 hours. The solar intensity follows a normal distribution where the highest intensity is reached at midday. The wind varies greatly during the day and has multiple peaks and lows. The residential loads follow a typical pattern similar to a normal household consumption. We can note the simulation speed here is sometimes slower during transient in the network. What we'll do in this example is make modification to another library component in order to improve its simulation speed for this type of simulation. The component we will modify is the diesel generator. In this example, we do not need to include saturation. We are therefore going to customize the generation block with the aim of removing the saturation algorithm. With the algorithm removed, we will gain a time advantage in the simulation. The first step is to change the model name to a new name. In this case, we'll rename the model Power V2G Custom. Next, highlight the synchronous machine block. Now we go to the MATLAB command window and run Power Customize. We will change the library name to Mode SM and then click Apply. A new library called Mode SM is created, which contains a customizable version of the synchronous machine. If we go back to the model, you will see that the synchronous machine is now pointing to our new library block. We will now modify the components saved in our custom library. To do this, right-click on the electrical model and disable the link. Right-click again to remove the link. This disconnects the electrical model from the main library. Double-click on the electrical model and then double-click on the synchronous machine continuous model. You can see that we have a components that calculate saturation and also switch elements that are a function of whether simulation saturation parameter has been selected in the main synchronous machine mask. We are going to remove all elements related to the selection of the saturation function. To speed up the presentation, I have already made the necessary changes in the model. We can now save this library block and it is automatically updated in our system model. When we compare simulation time of the original model with the model which includes the customized synchronous machine, we gain approximately a 25% time advantage. Please note that improvement will differ from model to model. When using customized model, it is best practice to document which components are customized. You can locate the customized block using the following commands. Replaying recorded data through a simulation model. Measured data is a powerful complement to the simulation environment. You can replay field data at any point of your simulation to investigate operational response, which may be difficult to capture using simulation models alone. A key example of this is replaying measured wind and solar irradiance data through your simulation model, thus helping you bring your simulation model a step closer to reality. In the vehicle-to-grid example model, you will see that we are feeding in synthesized data into the wind farm and the PV farm. We will now step through the process to show you how you can replay recorded data that comes from an external source, such as data stored in an Excel file. First, we will save the model as a new name, say Power V2G external data. Now that we have our new model, delete the current input for the wind farm and replace with an input port. We now go into Model Configuration and select Load from Workspace Input. You will see that the input is defined as a time vector t and a data vector u. These variable names can be modified as necessary. We are now going to read in some data from an Excel file. What we have here is active power measured at 15-minute intervals that has been derived from irradiance data over a period of a year in a location in the United States. To read this data into the MATLAB environment, we can use the following command. The command brings the data in as a table data. The warning you see is simply because MATLAB has changed the variable name to be valid. We can now plot this data. You see the profile over a period of a year. The difference between spring and summer is evident. We can zoom in to see the profile over a few days. Every peak corresponds to a day in the year, the flat zero to a night. We can see that there was some cloudy days in this zoom period of the year. If we zoom on a single day, we can observe partial shading occurring around noontime. We can now change the variable name to match the variable name of the external input data in the model. And we are now ready to run the simulation. I will not let the simulation run to its completion. We can look at some simulation result, let's say for the PV farm. We see that the transient after a programmed fault for the voltage, current, and total active and reactive powers. Note that the irradiance table provided data for a full year. This example simulates a 24-hour period. It means, of course, that we simulate only the first day of the year. We then could think to program a short MATLAB script that can select any day of the year from the table and simulate it in our example. That concludes this example. I'll now pass over to Graham, who will now talk about running multiple scenarios on multiple cores.
Thank you, Patrice. In this section, we focus on running multiple simulation scenarios and how we can use multiple cores to run those scenarios in a time-efficient way. For example, if we have 8 scenarios and 2 cores, then 4 scenarios will be run on core 1 and 4 scenarios on core 2. The more cores you have, the better. The example we will be looking at is the IEEE 123 node test feeder. I would like to acknowledge Bill Kersting's original citation. For more information on this network, you can follow the URLs shown. We are now in the MATLAB environment. The first thing we are going to do is open the IEEE 123 node model. This model was created automatically from a MATLAB script. We will use Rapid Accelerator mode to run this model on multiple cores. Select Rapid Accelerator and then save the model as a new name. We'll append the file name by adding _RA for Rapid Accelerator. Press Save. When we run multiple scenarios, it makes sense to run the model under a new directory in order to contain the data files that are generated. I'll make a new directory called RA1. Add this directory to the path by right-clicking on the directory and selecting Add to Path and Selected Folders, and then navigate to the directory by double-clicking. We'll now take a look at some important aspects of the model for running multiple scenarios. I'm going to zoom in to the inputs and the outputs. The voltage and current measurements are being saved to map files using 2 file blocks. This is essential when you are saving large amounts of data from a simulation. 2 file blocks incrementally save simulation data to file, and therefore limit the amount of RAM being used. We'll see in a few minutes that I generated approximately 70 gigabytes of simulation data running 1000 scenarios. Because I used 2 file blocks, I had no issues with RAM maxing out. The only limitation on data saving when you use 2 file blocks is the amount of space you have on your hard drive. We'll now step through the process for running the scenarios on multiple cores. I created a script that will do this, a script called run par4. Step 1 is to create a rapid accelerator target using the command on line 9. I'm going to run section and advance. As it's building the target, I should also say that you should make sure that you have no data saving mechanisms other than 2 file blocks in your model. You should also not include scopes, as they will slow the simulations down in Rapid Accelerator mode. The compilation will take a few more seconds. It's now building the target, and it's done. Step 2 is to create your scenarios. For the purpose of this example, I created 1000 scenarios by using random number generation to modify each load. The scenarios are contained within a data structure called ImpSets. See, there are 1000 scenarios. Each one has 21 timestamps and 152 inputs. Step 3 is to create data structures to tell Rapid Accelerator what to do for each iteration. So I'll just run and advance this. We'll now take a look at the setup for the first iteration. So here we tell Rapid Accelerator that we are feeding in input data called external input, that we don't want the up-to-date check to happen so that the model will not rebuild during the simulations. The simulation stop time is 0.1 of a second, and that we're going to change the file name associated with the 2 file blocks by appending the scenario number to the file name. So you can see _1 here. If we look at the second scenario, you see _2. So you see that the 2 file suffix has changed appropriately. Step 4 is to run the scenarios using par4, the parallel for loop. In this case, I'm limiting the scenarios to 8, and I have 2 cores on my machine. I'll run this now by selecting Run Section. As the simulation runs, we'll see the files being created in the current folder. So there we see the voltage and current measurements for scenarios 3 and 6. So par4 has decided to do scenarios 3 and 6 first. We see the tap measurements as well that are also being recorded. And as it runs through the par4 loop, we'll see the additional scenarios being added. Scenarios 2 and 5 have now been added, and so on as this progresses. So you can see it doesn't do the parallelization sequentially. Par4 will decide which scenarios to do on each core. We're through 6 of the scenarios now. Scenarios 7 and 8 to go. So it took 111 seconds approximately to run those 8 scenarios. So we'll take a quick look at the data. We're going to take a look at voltages from scenarios 1 and 5. So I can go down to the V-mesh, which is the voltage, double click to load that file up. We'll plot the voltage at node 1. So there you can see the 3 voltages, the 3 phases, and how the loads are changing and affecting the voltage measurements. We'll also look at scenario 5. First thing I'll do is load scenario 5 up. And we'll look at the same node, but for scenario 5. And we'll bring the 2 figures side by side. You can see the differences in the scenarios by comparing these 2 figures. Now we will look at working with large amounts of simulation data. A common challenge is that we have data stored on files on disk which are larger than the available memory on the computer that we are using. It could be that one file is larger than the available memory that you have, or you have a number of files that you've generated through Monte Carlo simulation, which, when aggregated, is larger than the available memory. In this situation, we can use memory mapping, where we have a pointer to the file, and once we have the pointer, we can extract only the data we are interested in from the file. For example, I am representing the data contained in 2 files here by the squares, and for example, we just wish to bring in the second row of each file. With memory mapping, we just index in to the files and extract the data that we need, and then we can stitch it together in some way in memory. Another option we have, certainly when we're performing statistical operations, is to bring segments of data in, and then once the data is in memory, we could perform a statistical operation on the data, which will generally reduce that amount of data. For example, if you're taking the mean value of a data vector, or if you're calculating standard deviation, or generating histograms. So let's take a look at a specific example. I previously ran a number of scenarios on the IEEE 123 node test feeder. I ran 1,000 scenarios, which generated approximately 76 gigabytes of data that you can see here. And if I go to MATLAB and type memory, then we see here that the physical memory that I have on my machine is 8 gigabytes. And so loading all the data into memory is not an option. So let's take a look now at how we can start working with this data. Contained within this directory, we have 1,000 files for current measurement. You can see each file here is just over 37 megabytes. I'll just scroll down. So you see 1,000 files for that. We also have 1,000 files for each of the onload tap changers. Then we also have 1,000 files for voltage measurement, just over 42 megabytes each. The first thing we need to do is generate objects which serve as pointers to the files. So we can use the map file function here because we are working with .map files. And what this loop does is it loops through the 1,000 scenarios and then generates objects which point to those files. Those objects can then be saved and you can reload them later and work with the files, so you don't have to run this section of code each time. It just so happens that I have run this previously. It takes a few minutes to generate the pointers, so I won't run it here. I'll now load up the file objects by double clicking on this file here, file_objects. Our objects contained within the parameter h, so if I do h and enter, you can see there it's just scrolled through all of them. I can access these objects by doing dot notation and tab. Tab here, I1, so if I just bring this one up, h.i1, this is the object associated with imes_1. So you can see here, properties.source, it lists the file, imes_1, and we can also access the variables within that file. In this case, there is one variable called imes, which has 477 rows and 10,001 columns. The columns are associated with time, the rows are associated with the current measurements within the simulation model. To access the data within imes_1, I use the object dot notation imes, and let's just say I want the first value, first row and first column, 1, 1, and there's the value, it's a value of 0, but I've not brought in the entirety of that file. I have brought in only that single value. We can take a look at some of the data in more detail, so I can do h.i1.imes, say 2, colon, so the second row, and we can take a look at that. I'll just zoom in. So this data was generated by just randomly changing the loads of the test feeder and running through 1,000 scenarios with randomly generated load data. So you can see here the currents are modifying, and step changes in loads are then causing these dynamic responses. What I'd done for this particular example was to index in to the voltage measurements and also the tap settings, and on each iteration, so as I'm looping through each of those 1,000 files, generating histogram data for each file and then aggregating it. So this is an example of reducing the data. So using a statistical operation, I'm operating on all the voltage measurements and all the tap measurements, and I am then aggregating the data so we can ultimately look at histograms of the measured data. Once you have performed your analysis, you can then generate a report by using publish. And I wrote a script which would basically just plot out histogram plots of each of the voltage measurements and the tap settings and generate a PDF from this. So if I go here to publish and edit publishing options, I've selected PDF. You see here the other options: HTML, XML, LaTeX, Doc, PowerPoint, PDF. And usually when you're generating the report, you would go to include code and set that to false, so it does not echo the code that you've used in the generation of your report, because the script you're writing to perform your analysis is also the script you're using for your reporting. And so set that to false so you don't echo your code that's performing the analysis. I've previously run the report. It takes a few minutes to run, so I'll just show you that now. So here's the PDF report. So what we have here are histogram plots of each of the voltages. So here for bus 1, we've got phases A, B, and C, and you can see the effect of tap changing going on. It's most pronounced in phase B here. If I scroll down, then phase B on bus 2, phase C on bus 3. And so what we have here is a very convenient way of generating a report with multiple plots, which would be extremely difficult to do by hand. If I now press tap profiles, got another section here on the tap settings. So the on-load tap changer between buses 9 and 14, you can see how it modified here over all the scenarios. Between bus 25 and 26, phase A and phase B tap settings. Tap settings between bus 67 and 160. And the tap changer between buses 149 and 150 is operating only on phase A, and we can see the impact there. In summary, we have looked at a number of aspects of performing power system studies. We've looked at how to configure the simulation model, as well as how to configure the ecosystem, the computational ecosystem that you have, which ranges from how you can replay data through the simulations, how to use multiple cores to run multiple scenarios, how to work with large amounts of simulation data, which is larger than system memory, and how to automate the generation of reports. Thank you very much.